in the lobby. That's okay. That's all right. Um, this is okay because it's a bad presentation anyways. Um, so just a disclaimer, um, we're not going to be doing a code along during this presentation just because assembly is a lot to digest. So we're more going to be covering the sort of like what is lower level in comparison to, upper level languages and stuff like that. Um, okay, so we can get started. So what is assembly, first of all? So assembly is a form of programming language that's the lowest level of abstraction in computers, and lowest level meaning the code is still readable by humans. Many compilers will translate higher level code that you're used to, such as Java or Python, whatever your bread and butter is. They'll translate higher level code into assembly instructions, which will then be converted into machine code, which is actually what's being, run by the processor. So assembly instructions directly translate into bytes that are then executed by the processor. There are many different types of assembly languages, and they're all unique to the CPU architecture. So there's different architectures in computers. You might be familiar with, Intel x86. That's a very popular one. Other CPU architectures like MIPS, they all have unique ways of it's all basically down to the physical level at this point of where the components are on the motherboard and how everything communicates with each other. So assembly itself is a set of instructions for the compiler, but they're all interpreted in different ways by different architectures. So why learn assembly? Um, it gives a better understanding of computer function. You're on a hardware-software interface at this point, and it's also beneficial for reverse engineering code. So if you're really trying to figure out what a section of code is doing, if you break it down into assembly instructions, you're seeing step by step what is kind of happening, um, or what you're actually telling the components to do. So when you code in assembly, you can potentially make your code go faster. And I actually have a few quips about this. So I'm not sure. I think some of you have taken 404 already. That's hardware software interface. I took it in fall of 2020 with Professor Phipps. And I remembered he told us couple of stories, 'cause as we all know, he's definitely got a lot of stories. But he told a story of when he was working on a piece of code in Unix for a job, right? And this is Unix, not not Windows or anything. So this is a long time ago. But the particular piece of code he was working on had to do date calculations. He was getting the date as a string from an input device, and he said that this was on a fast machine for the time, but that he was still unable to exceed 1,000 records per second. The code was written in C, and it should have been much faster for what it was doing. And at the time, open source was not an option, but he used a disassembler to look at what the code was doing. And I'll explain what a disassembler is in just a second. But it turned out that the date function um, looked to see what the current time zone was. And in order to do that, it had to open a series of files to see what the local machine configuration was, and then to compare that to a database of time zones. So once he realized that that was actually was what the compiler was doing, um, he was able to make a fairly simple fix. He made a one. He said he made a one item deep cache. If the current date then matched the date that he had just processed, he didn't call the operating system function that checked time zones. He just used the previous value. It cost a single string compare, but in return he got significant time savings. This was he said maybe 5 or 6 lines of code, and it tripled performance up to 3,000 records per second. So that's kind of the power of knowing assembly, even if you don't write it. Um, that being said, you're not likely to ever have to write assembly for for your um, your job. If you do, um, get a different job. I'm kidding, of course. Um, but it's it's certainly much more painful than higher level languages, but it does give you a pretty good understanding of the hardware and how it works. So that's pretty cool, I think. And another benefit to assembly is that you have access to machine features that are kind of hidden by higher level languages. So you're quite literally directly telling the CPU what to do. So that can definitely having that access will um, can be a benefit, and especially in the case of the story that Professor Phipps shared. And of course, if there are any questions at any time, feel free to stop me, or you can leave a question in the chat as well. So here's all the computer architecture knowledge in a brief summary. So this is especially covered um, in 404 and I believe a little bit in 333 as well. So just super briefly, um, so transistors, if we start with transistors, those are the most common electrical component. Silicone chips, such as your motherboard, that can contain billions of transistors. And you may have heard of Moore's law, that states that transistors get smaller about every 18 to 24 months, and you can fit twice as many per chip. So this means that computers get cheaper and more powerful. And you may be wondering, yo, I've got a computer on my phone in my pocket. That's pretty small. How are we going to make transistors even smaller, right? So this was definitely more of a thing in the 60s when it was first, when the law was first uh, theorized. It's not a rule. It's more of a rule of thumb, I should say. Um, so Moore's law is still valid, but its relevance has certainly decreased because there are new ways to measure processing power. Um, so you've in your computer, you've got your CPU, that's the central processing unit. This is basically the brains of the operation. It performs simple operations such as adding or comparing two numbers. And when you are running a program, the CPU is performing a fetch execute cycle. So basically you are fetching a instruction in the code and executing it. Pretty straightforward. Um, so in the fetch execute cycle, bytes of instructions are copied into the RAM, and the CPU is directed to start running at that first instruction in that area of RAM. So when you consider operating systems, um, these are set up to multitask so that you can run multiple programs at once. So each time you are executing a program, it has its own specific area of RAM that it's referenced by the CPU. And what is RAM? It is random access memory. So this is volatile and fast memory. It is where the program instructions are stored, as I just said. So volatile meaning that when you lose power to the system, you lose all the memory in RAM. So it's easy to access. It's close to the CPU physically, but it's not. Um, it's going to lose that information. For example, when you're working on a text document, you are changing bytes in RAM. That's why if you close out of Word and you haven't saved your document, you lose those changes to your document because it's volatile memory. And I guess as an additional example, um, for those of you who use Chrome as your browser, um, if you've ever opened um, uh, Task Manager, or I'm not sure of the Mac equivalent. If you've ever opened Task Manager while you're using Chrome, you may see that Chrome is eating all of your RAM. And why does Chrome eat so much RAM? It's mostly due to the plugins and extensions in your browser. Those are drawing more resources. But your 600 open tabs also aren't helping. So computer CPUs can handle billions of operations per second. I'm not specifically talking about microcontrollers; those are very small CPUs. But some of the more powerful computers can handle billions of operations. Um, Program files, just in case we've forgotten, uh, one millibyte is 1 million bytes. 1 gigabyte is 1 billion bytes. So your program file contains a certain number of bytes, and that is basically what is being executed by the CPU. All of those bytes are instructions. Um, so you've also got persistent storage. Um, this contains this is memory that is retained after power is lost. It's not as fast, and it's also not accessed quite as frequently as RAM. So this includes your hard drives and your flash drives, such as your solid state drive, USBs, um, you know, any sort of small flash memory. Um, and also contained in your persistent storage is your file system. And this allows system users to organize and track bytes of data in the form of your programs, your files, everything. And this basically just gives structure to your persistent data. So a microcontroller, which I will discuss later, is basically just a really small computer. It contains a small CPU, RAM, and basic storage. Um, so it's very, very small. It can fit in tons of different devices, like your microwave, um, stuff like that. Also, not sure how many of y'all grew up without cable TV. But in case you ever watched PBS, you got good old motherboard right there. Your motherboard is the chip in your computer that contains basically the brain, which is your CPU, your RAM, your storage. That's a fun show. Oh, blast from the past. All right, and any questions before I move on? No. Okay. I see we have several uh, new members in the audience. If you've got any questions, feel free to stop me. We're just covering basic intro to assembly. Okay. So to sort of cover what happens when we run a program. As I mentioned before, your operating system, that is sort of what obviously runs and manages all of your components in your computer. So it gives each running program its own section of memory and RAM, which is then accessed by the CPU. And it also handles multitasking. So if you think about it, you've got multiple programs running all at the same time. It's almost like a sandboxing kind of deal where you're keeping all of your programs kind of separate in memory, and so that um, they're all being that that specific memory is not affecting other program files. So any piece of software, your execute file, the .exe, that can be anything like your web browser, you know, your Visual Studio Code program. That contains bytes of machine code instructions that make up the program. Each instruction is about 4 bytes, um, and just as an example, an 80 millibyte software is 20 million instructions. So that's a lot of instructions. Um, so here's just an example of how a fetch execute cycle happens. So the CPU is going to access the instructions in RAM, which is then going to become the program of CPU instructions. Okay. If you take, we got a question in chat. If you take a picture of the sun and look at it, will you go blind? I'm not sure. Uh, maybe. Don't try it. Uh, thank you, Hafez. Very cool. All right. So what is machine language, right? So a CPU understands machine code or native code. And it's called native code because it's native to the CPU hardware design. So as I mentioned, each CPU series, um, because there's oftentimes multiple, different CPUs that have similar architectures, they all have their own machine code, which isn't compatible with other CPU families. Um, and all software is made up of millions of machine code instructions that do simple tasks like adding or comparing two numbers, for example, very basic things. And the machine code that of a CPU is basically hardwired into this CPU hardware design, and it can't really be changed. Um, so when you are writing your code in your higher level languages, Python, Java, all that stuff, C++, what's happening is that you're writing source code, and when you click run in your IDE or compile, the compiler is translating the source code into machine code instructions, which look very different. It's the computer is understanding your code in binary, right? Um, so when you are writing your code, it's again, like I said, your code is being broken into assembly language, which contains these very simple um, and quite confusing instructions. This is just a very small example of some instructions. Um, it is then fed into the assembler, which is then going to assemble these instructions into machine code, which is what I mentioned earlier in the story Phipps was telling about the disassembler. You're basically just disassembling your code into assembly, because assembly instructions are assembled into higher level code and disassembled into machine code. So, depending on the language that you're using, um, it might use a compiler or an interpreter. So, examples of interpreted languages are obviously Java, JavaScript, Python. They're considered dynamic languages and they require an interpreter. The interpreter looks at each line of code one at a time, executes that line, and then continues. Whereas the compiler will translate all lines of code first and then execute it. Um, C++, they're kind of partially dynamic. You, the programmer has to track memory use, so you're responsible for creating space in memory for your variables and also um, freeing that memory space after you're done with your um, after you're done with your data. And there's also, of course, the just-in-time compiler. That's kind of the best of both worlds. The interpreter is used for simple cases of code that is um, kind of easier, and then the compiler is used for more important sections of dynamic code, like nested loops. Okay. Any questions so far? We still you still with me? No, this is very riveting information. I know for some of our upperclassmen who've already taken 333 and 404, this will all be very uh, familiar, hopefully. So getting down to the nitty gritty of um, of assembly. Um, as we sort of saw in the previous slide, assembly is written in sets of instructions. And like I said, executable files are made up of millions of these instructions because all the instructions are just single lines that do one thing. You can have um, sort of not necessarily functions, um, but sections of code that can be named and then referenced again if you want to repeat that sort of logic flow or to jump to a specific section of code conditionally. But for the most part, you've just got single lines of code that just do one single thing. So with your instruction sets, you've got many different types of instructions, and they kind of all do different things. This is just a very brief overview. There's some CPU instruction sets have a couple hundred instructions. The 6502 that I'm going to introduce has only 56 instructions, so it's a very, very basic kind of assembler or assembly language, or assembly. Um, so it's definitely an easier one to start with. So you've got different types of instructions that all do different things, and remember we're breaking down these instructions into binary. So we're essentially just comparing numbers, just comparing, adding, doing basic operations on numbers. So you've got your basic bitwise instructions for logical and, or, exclusive or. Um, you've also got loading and storing instructions. So in your CPU, um, and I guess I'll kind of cover this a little bit more when we actually take a look at the microprocessor. But in your in your microprocessor, you've got registers that can kind of temporarily store data. And so, for example, loading and storing your um, you've got different components inside your CPU, the accumulator, the registers, your these instructions here, LDA, that stands for load the accumulator, LDX, load the X register, um, STA, store the accumulator, store the X register. Some of these instructions aren't going to make a ton of sense until we um, actually look at the block diagram and some of the examples of codes. So just kind of bear with me. This is more just the logic part. We've also got branch instructions. So these allow you to take a conditional statement and then perform certain tasks if, if the condition is met. So BEQ stands for branch if equal. If two, if two values are the same, we're going to branch. BNE, branch if not equal. Um, BCS stands for branch if carry set. So a another part of assembly instructions are your flag instructions. So these are basically just flags that signify different conditions. So you've got flags that um, will tell you if you've created a carry in your, your bitwise instructions. So for example, the flag C in your instruction is going to signify your carry. So if the carry is set, meaning if the flag C equals 1, we're going to branch. You've also got comparing instructions for comparing um, data. CMP is going to compare the memory and the accumulator, and CPX is going to compare memory and the X register. You've also got jump instructions. So you might have heard of go to instructions in higher level code, and it jump instructions basically are going to move the code to a different move the logic flow to a different section of the code. So in your higher level languages, go to statements are a big no-no, um, because it can create spaghetti code and you're kind of jumping all over the place and it's just not considered good practice. It's not the case for assembly. Your jump, branch, those are kind of go-to statements. Those are considered acceptable, and they're important for the logic flow of your program. Um, you've also got basic arithmetic instructions. Um, ADC stands for add to the accumulator with carry. So you're kind of adding uh, two numbers, basically, with your carry bit, which is either 1 or 0, if you remember your binary. SBC is subtract from the accumulator with carry. You've also got index registers, and you can increment or decrement those values. Um, INC is to increment your memory by 1, or INX, increment the X register. Same thing for decrease memory, decrease X register. You can also call instructions on the stack, which again is the form of memory. PHA, meaning to push your accumulator onto the stack. TSX, transfer stack pointer to X, the X register. A lot of these instructions do get kind of repetitive just because, this is my JoJo meme because I'm a fan of JoJo's Bizarre Adventure. Everyone watch it. Um, anyways, uh, I suppose I should explain this. Um, the ORA is an instruction in some assembly language, some assembly languages, for the logical or. Yeah. Anyways, um, also with assembly, um, you can also access different addressing modes. Excuse me. So, addressing modes are just basically different ways of accessing memory. So, for example, your immediate um, mode right here, that means that the number that you are um, accessing is going to be used immediately by the instruction, obviously. Another example, absolute mode, that means that the value given is the address of the value to be used. So just different ways of accessing memory, basically. And again, not a lot of this is going to make a ton of sense. It really breaks down to the individual architecture of the CPU, and it's certainly a lot to cover in a short amount of time. But this brings us to the um, microprocessor that I'm going to be covering in terms of assembly. So this is the 6502. It was launched by MOS Technologies in 1975, and it launched for $25, which at the time was 1/7 the cost of competitors. There was a big push at that time to, again, Moore's Law, make everything smaller and cheaper and more accessible. And so this microprocessor, along with some others of sort of its time, such as the Z80, this is kind of going to help inspire the home computer boom, of the mid 80s, early 90s. So, fun fact: this microprocessor is used in a lot of really popular um, or you know um, big name applications, like the Atari, the Commodore 64. If you've had a Tamagotchi, uh, that's the microprocessor in that. The Apple II. This is the Apple II is pretty much the most common application for why people are still using or learning 6502 nowadays. It was also the assembler for, um, I believe, all, if not almost all, of the NES games. Bender from Futurama uses the 6502 microprocessor, and also the Terminator uses the 6502. So, very cool. It is still used today. Um, a similar CPU in the same family, the 65CO2, is used in uh, embedded devices such as pacemakers. So again, very small device. It's only an 8-bit microprocessor with a 16-bit address bus. Um, so this is what uh, this is what it looks like. The image on the left is a generated image. Unfortunately, there aren't a lot of detailed schematics for for this microprocessor specifically, and basically it had to be reverse engineered. Um, very high quality scans had to be taken of the microprocessor in order to kind of break down what is happening here. But it's very cool. Um, and the different colors on the image to the left all signify, it's kind of color coded by component. So basically, you know, one color for transistors, one color for components connected by ground to a 5-volt power, um, that kind of deal. So the image on the right is a little more clear. It is the block diagram for your circuit inside your for all the components, excuse me, in the 6502. So um, this is where what I was all the instructions are going to kind of start to make a little bit more sense. Um, so you've got your accumulator here. That sort of is a form of memory that you push your computations to. Um, Here's another component of your CPU, your ALU. Um, I don't know who else took 404 with FIPS. I'm not sure if it's still taught the same way, but he had us write our own, basically, CPU, uh, including the ALU and all of the bitwise operations that are performed on that. Um, oh, as you can see, all of these components are structured in a very specific way. All of your individual CPU families are going to be structured differently, which is why assembly is specific or native to each CPU. Um, you've also got your stack pointer here, your X and Y index registers, um, and your um, address bus as well. Yeah, I'm not sure if there's going to be a ton of questions because this is a lot to digest. So again, I apologize. But hopefully it's somewhat of a introduction. And thank you, Theo. I've not actually read about people building 6502s in Minecraft, but it is probably possible. I'm not sure. But I mean, I have seen people build basic computers in Minecraft, so that's very cool, actually. Okay. All right, so the 6502, what the heck is going on here, right? So the 6502, again, it has the 8-bit accumulator. Um, it's got the two 8-bit indirect registers, um, the 8-bit stack pointer, um, and a 16-bit program counter. The program counter basically just um, points to where in your logic flow. The stack pointer, when you're using the instruction JSR jump to subroutine, you need to know where you're returning to when you're done. So that's where that comes into play. The X and Y indirect registers are general purpose registers which just hold data. They do have limited abilities, so they're not, um, they're just another component. The accumulator is what handles the logic and the arithmetic. Um, so the processor status as well, this holds the results of tests and flags. So as I mentioned before, you've got your flag instructions such as your bit for your carry, whether it's negative, whether it's overflowed, um, all those fun stuff. If there was an interrupt caused by a break, there's a flag for that as well, decimal mode, um, that sort of thing. So the 6502 can operate at clock speeds of 1 to 2 megahertz, and that's pretty slow. But the performance is competitive because it uses more combinational logic compared to other processors. So that's kind of why it's still relevant today. And um, add, it can address 64 kilobytes of memory. So pretty small. Okay, so now I've got some examples of 6502 code. Um, these two here are kind of more basic examples that you can probably pretty easily relate to some higher level code that you might have written. So the first example here kind of cuts off right there. Is an 8-bit countdown loop. So in your instruction, the syntax breaks down into the instruction code here. So, for example, LDX means to load the X register. And then, for example, that specific instruction is going to be loading a address in memory um, with a number. So even though we are assembly is translating into machine code, which is binary, um, we can use, we typically use hex in assembly to represent numbers. Um, that's typical for assembly. Um, the processor will is able to recognize binary and decimal and hex as the same value. Hex is standard. It's the most concise. Just be consistent with it. Don't go using different data values just because or um, bases just because you can. So with the 6502, bytes go from 0 to 255. So that's what we are loading into the X register here. And hex numbers in assembly are prefixed with this $sign. That just tells the processor that this is a hex number, not an address. When it is combined with uh, the I don't know, pound or uh, the hashtag, whatever you want to call it. So the next instruction here, this indicator over on the side here, loop, we are going to start looping between this line here until we get to the next line. And then we've got this branch statement here. So we're going to start we're going to load X with 255. We are then going to decrement the X register by 1, and then that is going to then decrease it to 254, for example, and then we're going to read this branch if not equal statement here. So if X is not equal to 0, then we're going to branch to the loop section here, and then we are going to decrement again. And then if it is 0, we are not going to return to the loop. We are then going to return to the main section of the code, basically. So that is a very, very small bit of code. Obviously, it's only excluding the loop there. It's only 4 instructions. So considering that code is millions of machine instructions, that's a very small piece of code. In that example, specifically, how does branch if not equal know that X is 0? It doesn't. It only knows that the flag, the Z flag specifically, is set or reset. I didn't exactly cover all of the flags. There's different ones for different purposes. I can provide the full PDF with all of the instructions, all 56 instructions on that in the workshop text afterward. But basically, the Z flag is going to be set or reset if the X register is 0. So that's how it is checking for whether or not to loop again. It's not actually seeing whether X is equal to 0. So that's the logic behind that one. Does it kind of make sense with the instruction codes? It's a lot to kind of digest again. But I don't know, I think it's kind of cool. All right. So the next example here is deleting an entry from an unordered list. So as I mentioned, you can sort of label sections of code so that you can jump around to different sections conditionally with your jump or branch instructions. So this is just kind of an arbitrary name. The first instruction here is to load the Y register, and that's fetching the element count. Then you're going to load the accumulator with the element count and hex value of 30. Then a transfer, and then we're going to load the accumulator with the next item here to delete. And remember, in these instructions, you kind of have to read them carefully. So we know that this is a hex number, obviously, because it's got this $sign in front of it. But it's different from, say, the LDX FF up here, because this £sign hashtag is signifying that this hex value is a number, not an address. All of assembly deals with addresses and numbers, so if it does not have that hashtag, it is specifically referencing a part of memory. So then this next section of the code here, it's comparing the index to the next element in the list. Um, if it matches, we're going to branch if equal and delete, which this is in a different function. We're going to move to a different part of the code that is called delete, where the actual instructions for deleting that part are. And then if not, just decrease the element count. I'm sure you've all dealt with data structures in higher level languages, and you can similarly delete those elements from that unordered list in higher level languages, but obviously it doesn't quite look like this. It looks a little more readable, right? But that's essentially what is happening when it gets disassembled into assembly code. All right, any questions on this so far? Okay. And again, we're not actually going to be coding in assembly because it's a lot to process. But I do have something cool to show you once we go over this next example here. This is an example which is going to return an 8-bit square root. So for this specific example, it's based on the observation that the square root of an integer is equal to the number of times an increasing odd number can be subtracted from the original number and still be positive. So that sort of breaks down into these sections of code here. We are loading our Y register. This is the stack. Wow, yeah. So obviously it's not very readable, but once you start to recognize some of the instructions, it is a little clearer. And actually, I can show you an example of the actual data sheet. So with all of your, I forget, am I? Okay, hang on just 1 second. All right, so with all of your, hang on, can you guys see that? Yes, okay, great. So as with all of your uh, different assemblers or different assembly instruction sets for your different CPUs, there's going to be a giant PDF for that processor. So it will give you a basically a diagram, and this gives you information for addressing, as well as just a lot of specific hardware information as well. Clock cycles. We're really getting down at the low level here. But this does matter because assembly does work very closely with um, your components, obviously. So you do want to keep that in mind if you're doing some very, very specific stuff with your components. So this is the full instruction set for the 6502. Um, so gives you a lot of options here from the Aura. JoJo reference there. Um, but yes, so this is a um, lot of information. It's also really hard to understand coming from higher level languages as well. Um, and here's an example as well. You've got this is if you remember from one of the previous slides, the actual image of the microprocessor was just a little chip with all those little pins. If you're actually playing with a microprocessor on a breadboard, which highly recommend, very fun. Um, I mean, as much fun as compiling code is and getting it to actually compile. Um, it's also fun to play with electronics components. So all of these here, you've got your address bus right here for addressable bytes of data. You've got um, your power pins as well. And I wanted to show an example of a pretty cool simulator that will show you what the chip looks like in action. So let me just get that sign up as well. Oh, here's a resource for you. Don't download more RAM. You can't. It's a joke, but it's a fun joke. Anyways, so this is visual6502.org. They have a very cool JavaScript simulator, which I believe is now HTML5. But this is just showing you as it these and I'm sorry, this is a little bit of an eyesore. uh, um, maybe don't look at this if you I don't know, get seizures. Um, but each one of these colors represents again the different type of components, your transistors, your components that are accessing ground and your 5 volts, that kind of deal. Each one of these um, this represents the memory in your 6502, and as we run the simulator, you can see it's highlighting. Again, it's going very fast, but it highlights the different parts of memory that are being written or that are either being read or written to as the program runs. So I think this is a pretty cool simulator. It's a little hard to understand what all these colors mean, um, but pretty cool actually. And there's even an advanced page if you actually end up taking a look at the visualizer, and you can find different components as they're being um, like where it is on the chip. And yeah, so it's a pretty cool simulator actually. So that is a very rough uh, introduction to assembly with the 6502 microprocessor and its instruction set. It is a very short instruction set, only 56 instructions. So if you're looking to get started with assembly, that is a great place to start. Um, are there any questions about assembly? Or yeah, it is a really cool uh, a really cool visualizer. And um, James, I mentioned earlier that the 6502 specifically does not have a lot of surviving schematics. So all of that was very heavily reverse engineered, like taking very high quality GANs of the actual chip itself um, to try and figure out its logic flow there. And also, that is a great reference as well for x86 instructions. Um, x86 is definitely a lot more complicated than the 6502. Um, it's probably a little less fun, I'm not gonna lie, but it is a very popular um, instruction set for the Intel x86 chips. So definitely, yes. Yeah, pretty much. It has more registers than the 6502 has instructions. Exactly. So it's definitely a much, much bigger chip. Again, these are the 6502 is what's going in your pacemakers and your, you know, your Tamagotchis. So definitely a much, much smaller chip, but it still is very cool. Um, if anybody is interested in more information on what is going into these instructions and the actual physical hardware of the chip, I've got a bunch of resources for that as well. Does anybody have any questions on
Hello,
assembly?
am I audible?
Yes, you
Can
are.
I be heard? Okay. So I'm sorry I missed the beginning of the workshop. I copped in right at the end. Looks like everything went well though. Very interesting workshop. I did miss so is the 6502 assembly language when it's translated into machine code, is it variable length instructions or fixed length? Like, do they like you know how MIPS? I don't know who here knows MIPS, but when you guys learn MIPS, which I don't know who's learning MIPS here now. Didn't they just do MIPS for 404 or something? Is
Yeah, I
Dan
think.
D in the call?
I think-
Dan,
Yeah,
you
we're
just
doing
who's
MIPS.
doing MIPS? Okay, okay. So MIPS have fixed 32 bit. MIPS instructions are always 32 bits. Is 6502 fixed with? You know
I
this off the top of
I
your head?
I believe it's fixed. Um,
Okay. I'm wondering if it's fixed 32 bit. I have to look this up. 'Cause this is ideally, so we have you told the kids that we have 6502 kits for a 6502 workshop at some point?
we yeah, that is in the works, and we've not actually
We don't know when we're doing it, but
finalized the details, but we are going to be doing a build a 6502 8-bit CPU using Eater kits, and so that's very cool. That's kind of why I specifically chose the 6502 for this
just a good
workshop.
idea.
Yes,
6502 VGA is next semester, but 8-bit CPU is this semester.
excellent.
I believe the 8-bit CPU that Eater makes is heavily inspired by the 6502 instruction set, though, so we're gonna be pretty much set.
Good
Y-
stuff.
yeah, and Theo makes a good point. In advanced mode, it does allow you to kind of narrow in on some of those components. And actually, here is a link that pretty much breaks down the um, the visual circuit into much more detail. Um, and this is if you are interested, it's great for even if you don't understand lower level electronics. Um, it
Oh
really
wow.
breaks things down. Yeah,
Oh
this is
my. This is incredible. I don't think I've ever seen a resource this good.
Oh yeah,
Like
this.
they're really like laying the gates on top of everything. This is so cool.
Mm-hmm. Oh, I've got
Oh man.
tons of links for fun things to do with 6502. More information with the, here, I'll give you the link for the simulation as well. And actually, let me try and find it here. I know they,
Wait, Theo, you can click in advanced mode and turn wires on and off? Oh, you can. That's insane. Oh, that's really cool. Oh,
there's a link
that's
for
really
the
neat.
simulator as well. Go
That
ham.
simulator is insane.
Yeah,
I had
very.
seen that this simulator existed, but I never actually used it. It's very neat.
And actually, as well, on the advanced mode, you can also, if you want to try your hand um, at 6502 instructions, you can input it here and trace your code. So that's pretty cool as well. Um, another fun thing that's happened recently in the 6502 world is the is the monster 6502. Um, so here is the web page for this. I know they were going to be taking this thing around to like, nerdy conventions and showing it off, but that was put on pause for COVID. Um, but they made they again, like I mentioned, how they had to reverse engineer the chip to create the visualizer, and actually most emulators for the 6502 as well. Um, they created a working transistor scale replica of the classic microprocessor. So you know how the um, hiding here, but if we bring it to, this is what it looks like, right? Super small. Obviously not super small, but that's essentially what's going on inside the actual chip, which we can kind of see with the visualizer as well. Um, but this thing is huge. It is 12 by 15, um, with a total of 4,769 components. So, are you nuts? Probably. So yeah, if you ever want to go to maker fairs or nerd conventions, you can see this giant chip, which is very cool. And this thing is actually slower than the original chip, but that's kind of due to the size, partially. But it's cool to see the chip kind of broken down and kind of really get into the to the nuts and bolts. And actually, this is I'm really excited for the 8-bit CPU workshop as well. I think that'll be really cool. Yeah. So, any more questions about assembly? It should be renamed to Bro language. Yeah. So again, um, you're probably never going to have to write in assembly for your job, um, but it is certainly interesting to understand what you're writing in code and how it breaks down in the actual computer
But for
into
the
binary.
joyride, if you want to be like the people that rode Roller Coaster Tycoon, be my guest and write an entire game in assembly.
Yeah, yeah. I mean, yeah, like I said, the NES games were written in 6502. You can do a lot with it. Roller Coaster Tycoon is very fun. Like making it go off the rails. Um, yeah, I I think it'll make it makes a lot more sense once you actually really delve into the architecture of the chip. And like I said, this is what it looks like with all your pins and but it certainly is a lot to digest. So I will gift you this wonderful chunky PDF in the workshop chat as well, in case you're interested. And if you do actually want to get into writing assembly, there are tons. My computer would stop bugging. There are tons of emulators online for similar to the visualizer that are all good at showing the code. Or you can actually get your hands on with the little microcontroller. They're super cheap. The little Sunfounder kit. Good stuff. Good stuff. This pretty much concludes my assembly workshop. If anybody's got any questions, I'm happy to answer questions. Otherwise, you're all kind of free to go. Or hang out too. That's also very cool.